This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So also from my end, welcome everybody. It's so great to see so many... Can you hear me? Okay. Yeah, that is indeed better. Yeah, a big welcome to everybody also from my end. It's so great to see so many faces that I have seen already at past QTML versions and also many, many new faces here. And now, without any further ado, I would like to invite Marco to come up here.
Do we have a clicker by any chance? No, it's fine.
Okay.
I'll just stay here then.
Okay. So, real quick, oh, okay.
If this is hard, I'll just not do it.
We'll figure it out, wait.
I think it's in the back of something. I don't know if it's going to work. So there's this back on the back of the computer. You might be able to see this. Yeah, let me check.
Ich mach quickly do still the intro. Sorry.
Sorry.
Don't worry. Okay, we're figuring this out, right? It's the first session. Please bear with us here. So just a real quick introduction, right? So Marco Cerezo is a Guatemalan physicist who is a staff scientist right now in Los Alamos for some time, where he's doing some great work to understand many things about learning theory and quantum machine learning in the variational sense especially, and also very strongly he's trying to figure out what are the limitations of those systems, which is what he'll actually talk to us about right now. And with that, please, Marco.
All right, can people hear me well in the back? Fantastic. Thank you very much. I'm very excited to be here. I want to thank the organizers for the opportunity to share some of our works, and I'm very excited to get this party started. So today I'm going to be talking about absence of barren plateaus and classical simulability. If you were at last year's QTML, this was kind of hinted at. So today this is going to be like the end of that story. So the summary of this talk, I'm going to very briefly discuss barren plateaus, what they are, how they connect to classical simulability, some caveats in our arguments, and some new opportunities that are coming from this. So to be honest, I need to give a few disclaimers. The first one is that the talk is pretty self-explanatory. Does absence of barren plateau imply classical simulability? Yes. Do we need to rethink variational quantum computing? I personally think so, and that could be the end of my talk. But this is not what I want to do. I actually want to run you through the thought process that got us to this realization. And the overarching theme is that sometimes we need to take a step back from what we're doing, stop looking at the tree, and start looking at the forest. And this is hopefully what I want to try to teach you today. So second, this talk is going to be very opinionated. This is not a bug, this is a feature, because this is precisely the community where I think we need to have thoughtful discussions about what it is that we're doing. Is the setting variational quantum computing, quantum machine learning well defined or not? I think that this is where we need to start having those discussions. Also, this talk is going to have memes. A lot of memes. Like, honestly, way too many memes. And for a second there, I was very worried that the minister was going to be here, and I'm going to be like, oh, this is going to be shameful. They're going to be like, what are we putting our money into? So I was like shaking a little bit. So without any further ado, let's talk about the hype of variational quantum computing. So this technology, you have a problem that you want to try to solve, and you're very keen on putting it inside of a quantum computer. Now, to solve it, you need to program the quantum computer. You need to place gates, you need to initialize some state, and make some measurements. And we usually don't know how to do this. So the typical approach is we will use the learning methodology. We're going to take the problem of interest and code it into an optimization task, and try to train a quantum learning model to solve this task. And what you're going to hear is that why would we ever want to do this? Because the quantum computer has this very large Hilbert space, which we can use as a featured space for data processing abilities. And this is kind of like the typical scheme that you might see everywhere. You have a problem of interest. You're going to run some states through a parameterized quantum circuit, which has some knobs that you need to tune to try to solve your problem. You're going to make some measurements. You're going to use those to compute a cost or loss function that quantifies the degree to which your problem has been solved. You're going to give this to a classical optimizer that is going to give you the next set of parameters in your parameterized quantum circuit, and you're going to run this loop until you get convergence and you're happy with how well you're solving the problem. Now, this technology, there's many applications. For now, I'm going to focus on tasks where at the core and the end of the day, we're going to be computing quantities of this form, which is like take a quantum state rho, send it through a parameterized quantum circuit U, and measure some expectation O. Of course, you can have multiple of this parameterized quantum circuit, or the state can depend on some classical data, but this is just for simplicity. And if you have multiple of those, you can classically combine them to get mean squared errors or other quantities, but at the end of the day, this is the thing that we're extracting from the quantum computer. So there is a lot of interest in this technology. A few days ago, I went into Scopus to see how many papers are doing VQE, see this very nice curve, QAOA, and quantum machine learning, which is why we're here. This is just off the tracks. And a lot of claims out there about we can get a quantum advantage with quantum machine learning. And my question is, how certain are we of this? And if we're not certain about this, why do we see this upper curving trend? And I think that a colleague of mine, Zoe Holmes, gave this quote, which I really like, which is that in a way, variational quantum algorithms have democratized quantum computing. It's actually very easy to do variational algorithms. You can take any problem that you like and create a variational algorithm out of that. And then if you know a little bit of Python and linear algebra, you're good to go. The learning curve to access quantum machine learning is fairly easy. But for me, the important question is, what can we distill from this? What do we have to show for variational algorithms when we're training parameterized quantum circuits? And to be honest, it is very hard to tell. And I could, and likely have, spent multiple hours talking about the limitations of this technology. Here are some, but not all of the problems that this technology have. And today I'm going to be mainly focusing about barren plateaus and classical simulability. If you want to discuss some of those other problems, I'm going to be here all week, so feel happy to approach, and I'll be very happy to chat about some of them. So, barren plateaus. Who here knows what a barren plateau is? Okay, fantastic. So this is great. I remember like 4 years QTML ago, I was like shouting barren plateaus, and I think maybe just 10% of the people knew this. So we've spent almost 6 years thinking about barren plateaus. And again, what I want to try to convey here is what are the lessons that we've learned after spending so much time thinking about this technology. So initially, we envisioned barren plateaus as kind of coming from different sources. There's a lot of things that gave us barren plateaus. But after a while of thinking, I think that now we have a pretty good understanding of this problem. We actually wrote a review on barren plateaus, so if you're interested in more details, I encourage you to read this article. But what I can say is that barren plateaus are a problem arising from a curse of dimensionality. So again, we had all of these methods that had barren plateaus, and we asked the question, why do they all have barren plateaus? What is the underlying mechanism that is making us not be able to train them? And the thing is that it was there from the start. If we look at our loss function, which is just this inner product, now this is just the Hilmer-Schmidt inner product between parameterized state and measurement, or vice versa, initial state and Heisenberg-evolved measurement operator, think about this as vectors in operator space. So decompose rho and O into Pauli basis, now they are vectors of length 4 to the n. And what you're doing is just computing their inner product. So the loss function is a similarity measure between two exponentially large vectors. And this should start raising some red flags. Because if you have some exponentially large space, and I give you two random vectors, and when I say random, it's I randomly initialize the parameters in my circuit, those are bound to be exponentially close. Their overlap has to be exponentially small and exponentially concentrated. And this is a fairly general phenomenon that occurs under very general conditions. So just like that, we can see that, barren plateaus are a curse of dimensionality. And the thing is that we can ask the question, okay, so how do I know if my model has a barren plateau? And we can review some of the known results in the literature and recover this curse of dimensionality by asking, take the Heisenberg evolved measurement operator and just ask, where can this guy go? Just Heisenberg evolve it and see if you can reach exponentially many operators. So if we take the original Google paper, which says if you have very deep circuits, which are very expressive, maybe there are two designs. I take any measurement operator, I Heisenberg evolve it, I can get to any other operator. So this explores an exponentially large space and has a barren plateau. What about shallow versions of circuits, like this hardware efficient ansatz where you act on neighboring qubits in this brick-like structure? I take a global measurement, kind of like X tensor n, and it's very easy to see that even if this is just single qubit rotations, I can transform any global Pauli into any other global Pauli. So that's at least 3 to the n operators that I can get. 3 Paulis on the first qubit, 3 Paulis on the second qubit, 3 to the n. So this is also exponential and also has a barren plateau. So you can take all the 30 pages of appendices in this paper, replace it by this, and it's kind of like the same idea. Now, what happens if we have a shallow circuit with a local measurement? You ask the question, where can this measurement go? You Heisenberg evolve it, and now you see that I can only get 2 operators in this light cone. So if my circuit is shallow, say log n depth, I can only go to log n qubits. And how many operators are acting on log n qubits? Polynomially many of them. So this explores a polynomial subspace and indeed avoids barren plateaus. So it's very natural. Of course, there's a lot of things behind this, but to give you an intuition, I think that this is a very sane assumption. So we have seen this architecture that doesn't have barren plateau. And again, there are many architectures out there that provably don't have barren plateaus. And the thing that we were wondering is, what do they all have in common? Again, the theme of this talk is, let's stop looking at the trees and let's start looking at the forest. And what we realize is that all of the architectures that provably don't have barren plateau is because they're acting in a polynomially small subspace, kind of like this thing that I showed. And you can actually take a bunch of circuits that don't have barren plateaus, you can find the subspace where you're operating at, and this is very interesting because we can see that if you don't have barren plateaus, you live in a polynomially small subspace. But of course, the immediate realization is, if I live in a polynomially small subspace, which I know which one it is, why shouldn't I be able to classically simulate this? And this was the end of last year, at last year's QTML, this was the realization that I was struggling with. And honestly, if you see this paper, it has a bunch of authors, because I was discussing with people on QTML, and I was like, where is the bug in this reasoning? Just like, what are we saying wrong here? And we realized that the more we thought about this, the truer this became. So this is the other claim that we have in this paper, which is now that if you have a problem that lives in a polynomially small subspace, you should be able to classically simulate it. And let's take a step back and see what it is that we've said. So we have this archetypical architecture. We have a problem, you put it in a quantum computer, you iterate back and forth, and this gives you the loss function. But what do we mean by classical simulability? We mean actually something that looks like this. So you have a quantum computer. I'm going to give you access to this quantum computer for an initial data acquisition phase. This takes no more than polynomial time, and you can make measurements and store them in a memory that is no more than polynomially sized. And once this initial data acquisition phase is over, you're no longer granted access to the quantum computer, and you should be able to produce the loss function for different sets of parameters without having access to running the circuit on the quantum computer. And what we showed is that a lot of the barren plateau-free models are actually here. But what's key for me, and this is very important, is that the quantum computer is still needed. And to illustrate this, let's go back to our example. Imagine that you want to compute the expectation value of a state that is going through this circuit. Well, this is just a unitary acting on log n qubits, completely classically simulable. But then if I give you an arbitrary state, how are you going to get the expectation value on those log n qubits? Well, in general, you can't. But if I give you a quantum computer initially, you can just do shadow tomography on those states. And this was actually first reported in this paper by Chris Ferry's group, where you can just compute the expectation values given the shadows of the initial state. So this is very clear that you do need a quantum computer. And of course, before anyone goes on and says, oh, but if I have a variational algorithm whose loss function is not concentrated, it's not possible that everything is classically simulable. Of course it isn't. And we can actually just build this. We try to take a step ahead, and we did it ourselves. We can construct an artificial variational algorithm that encodes Shor algorithms in it. It doesn't have barren plateaus, and it's not classically simulable. Sure. Is this interesting? I don't think so, because this doesn't resemble anything that we do in practice to solve problems of interest in quantum machine learning. So I can consider this kind of a worst case scenario. So worst case, non-classical simulability, completely expected. I'm not surprised by the fact that we can construct these things. But now we can ask the question, what about other notions of the quantization and classical simulability? Because we've already seen that worst case, definitely not possible. So maybe I tell you, I want you to estimate the loss function on average. I sample some set of parameters according to some distribution, and you need to be able to produce an estimate of the loss function that is epsilon close in average to the true one. But maybe you say average is not interesting. A quantum machine learning model, average set of points are not interesting. So maybe I want it for all sets of points. Or maybe you're pragmatic and you tell me, you know what, if you give me that initial data acquisition phase, I don't care that my loss function is epsilon close in average or for all points. I just care that I'm going to take that data, do some simulation, and solve the task. And if I solve the task with my simulation just as good as you would with your quantum computer, then this is also dequantizable, right? So it turns out that average classical simulability is very easy. You can just pretty much simulate any quantum circuit without a lot of problem. And I urge you to look at this paper. But again, average case is not practical. Just like worst case is not interesting, I think that average case is not practical for solving problems. So what about non-average case? And I think that this is where you need to go to a case-by-case analysis. So for instance, if you have a circuit that has Moley algebras, you can do the simulation for all theta. I'm not going to get into this because Matt's going to talk about this immediately after this talk. And Matt is great. Matt is hiring soon, so hire Matt. Then let's talk about something where we're going to take this pragmatic approach. Quantum convolutional neural networks are promised as one of the most useful circuits because they don't have barren plateaus and they can be used for pretty much anything. And the thing is that they're technically quite expressive. They can transform any Pauli into any other Pauli. So they explore an exponentially large subspace, and yet they do not have barren plateau. The reason why is that this guy, whenever you look at it, Heisenberg evolves, in average, is just local. So whenever you randomly initialize a QCNN, it's just looking at the initial state locally. Now, again, this is average. It could happen that during training, you leave this classically simulable regime. But what we see is that this is not the case. These guys, for all the problems that we have out there in the literature, we can just simulate a QCNN via backwards propagated Pauli path truncation algorithms. And we can just solve with this QCNN that just looks at the initial state locally if you give me access to classical shadows. In some cases, we don't even need those classical shadows because the whole pipeline is simulable end-to-end, such as classical data. So if you ask me, I don't think that QCNNs are doing anything quantum, pretty much ever. I'm also happy to be able to be proved wrong, but again, I want to engage in this discussion, but at this point, I don't think they're useful, and also they're not convolutional. This is a pet peeve of mine, that there's nothing that is a convolution in there. And if you want to fight about this, go see Pablo's poster. I'm going to have him be my champion for this. So from here, what are the caveats in the arguments that we're giving? The first thing is that, again, it's not that anything that is not concentrated is classically simulable. It is a little bit of a mouthful, but I think I said it right. And we've already given this problem that encodes Shor's algorithm. This is not classically simulable. This doesn't have a barren plateau, but it's not like what we do in practice. And why is this breaking our initial assumptions? It's because it's operating in an exponentially large space, but it's doing this in a very orderly fashion. The gates are placed in such a way that we know exactly what we're doing. In Shor's algorithm, in QFT, in quantum phase estimation, we're not just randomly throwing gates in there. And Scott Aronson says this, where quantum computers, you need to carefully choreograph the patterns of constructive and destructive interference in a quantum computer. Is a variational algorithm doing that? I really don't think so. So we need to be careful about what we're doing with quantum algorithms. Then, our proofs rely on absence of barren plateaus, so that means that you could have large gradients, but we can't identify the subspace to simulate. This could be what's happening with warm starts and smart initializations. I'm not terribly certain that that's true. Smart initializations, I don't think we're special, and we're actually working on trying to show that there's exponentially many ways to initialize a computer with large gradients. So now you're pushing the complexity of, oh, I initialize with large gradients, let me train from here. But if there's exponentially many such initializations, which one's the correct one? And I think you're just pushing the complexity somewhere else. We also have a paper with Zoe Holmes where we show that pretty much generically, if you give me a region of a landscape that you're interested because you started next to the solution, we can also classically simulate this. And that paper should be coming out, I think, at the end of this week. So, of course, we're basing ourselves off expectation values. Generative models don't necessarily fit here. So if you're interested about further dequantizing quantum machine learning, this is an open question. And there's some very fundamental differences between computing expectation values and sampling. So I'm just going to leave it at that. Some new opportunities from our work. We still need quantum computers. So this, for me, is really great because it means that, we still can get a quantum advantage. And also, just because we can simulate the laws doesn't mean that it's practical to do so. So maybe we can still get some very small order 1 improvement by running stuff on a quantum computer, but we need to be aware of those classical simulation methods. And again, these algorithms, you don't need to run them in a quantum computer. You're just giving a classical algorithm data. And there's not one classical algorithm to rule them all. So just maybe exploring this is going to lead to more quantum-inspired classical simulation algorithms where we're feeding them with classical data. And this leads to questions sort of like, classical training, quantum deployment, is this useful? But also more interesting, what is the role of data? And I highly encourage you to look at this paper, The Power of Data in Quantum Machine Learning, where they show that if you take classical algorithms equipped with measurements from quantum computer, those can be strictly more powerful than classical algorithms. So the fact that our quest to understand quantum machine learning took us to this paper, just completely orthogonally, I think it says something. And I think we should listen to the math. And what is the outlook of this talk? I think that we really need to rethink about what it is that we're doing in quantum machine learning. Is this classical simulability a symptom of a deeper issue? I don't know, but I think we at least need to acknowledge that this problem exists. I think that thinking outside of the box and not doing, streamline, putting a parameterized quantum circuit and training it will lead to new and exciting directions, especially when we take into account the power of data. And to finish, I want to quote this piece of this really nice article by Maria Schulz's group, which is that, what do we want to show? Do we want to show that quantum machine learning works, or do we want to ask the question of whether it works? And those are two different questions, because if you set out to show that you can get a quantum advantage, you will be able to do this. But I don't think this is the way that we should tackle it. I think that we should ask the question, is this going to lead to a quantum advantage? So I think you need to be careful with positive bias in your research. And with that, just very quickly, Zoe and me are being guest editors for a QST article where we want to talk about the future of variational quantum algorithms. So if you have some strong thoughts that maybe are not fit for a paper and you want to just write a perspective, let me know. If you have some new ideas, maybe half-baked, some benchmarks that are showing, hey, variational doesn't work, where can I publish this? This is the place. We want to see honest benchmarks, half-baked ideas, all that stuff that you wouldn't send because you're not sure if it's going to get in. We want it here. And finally, we run a quantum computer summer school every year. I think applications are going to be open this week. We're going to try to get some Lanel folk to give you the link for that. And I think that the nice thing about being the first author, the first lecturer of the school, of the conference, is that from here onwards, I can just chill like this koala whose picture I took over the weekend. And thank you very much for your attention.
So we have some time for questions. Thanks for this great talk, Marco. I already see one in the back, so maybe we can...
Oh, is that Nathan? I'm worried.
Hey, Marco, fantastic talk. I hate to say this, but I totally agree with everything you have to say. I know, it's totally out of character. But one thing on kind of a more positive note I wanted to ask, if there are these obstacles and this low barrier of entry for people getting into QML via variational algorithms, what would you propose in the light of your learnings that people should do differently in order to be able to get into the field if this isn't as promising as we previously thought?
This is a great question, and I actually had this on the Outlook and I removed it for time constraints, so I really thank that question, which is that if someone asks me and they say, I want to do variational algorithms in quantum machine learning, I would say totally, go for it. I think it's a great way to learn about some of the subtleties of quantum information. You're going to learn about some of the issues that arise from having a lot of entanglement, from having random quantum circuits. Personally, for me, when I started in this field, I was doing variational algorithms, and this had been a path to learn so much about random matrix theory, representation theory, quantum information. So I would say absolutely go for it. Just try to keep deepening your knowledge, because I think that at the end of the day, quantum machine learning, I'm not certain that it's going to be a transferable skill like classical machine learning. If you know classical machine learning and you're doing some application, the day after tomorrow you're in a new job, those skills are transferable. Training parameterized quantum circuits, I'm not really certain yet, but if you learn quantum information, rep theory, statistical learning theory, those are tools that you can use in other places. So I don't know if that answers the question.
Hello. Hi, Marco. Thanks for the talk. It's so nice to see how your argument on barren plateaus evolved, or the way you talk about it from at the beginning, a couple of years ago. We need a lot of mathematical tools to explain it, and now you can just say, okay, makes sense. It's exponentially large vectors. Their overlap will be zero. So that was really cool. Just a quick question. So I always thought like variation circuits were never super interesting as a model, but there will at some stage in my mind, even in fault-tolerant models, be a little part that's learnable. So I think the techniques will probably survive, but for a completely different purpose. And my question would be now, what if, for example, you've got a variation circuit, but then you've got some routine like a quantum Fourier transform or phase estimation and barren plateaus. Maybe you've got an intuition immediately that says, okay, unless you sample, this is also not really interesting.
So I think that we've thought about this kind of like variational algorithm being a part of a larger pipeline. But my personal problem is that you still need to make that part of the pipeline work. And if that part of your pipeline is not working, and if you don't have the correct inductive biases, you have a model that is too expressive, it could lead to issues, but I completely agree. Maybe you do something that is classically simulable in expectation values, but not in sampling, and then you use those samplings for something else. This is the kind of thinking outside the box that I think we should keep doing. So yes, I think there's a lot of opportunities for variational algorithms. I don't think they're dead just yet. I don't like making big claims, only the Sith talk in absolute, you know, so until I have like absolute proofs, I'm not gonna tell anyone, don't do this. But yeah, there's potential places for applications, completely agree.
Okay, let's do two more quick questions. I saw one back there and one over there, and then we move on in the program. Great.
Shall I? Very quick one. Hi, Marco. What kind of classical shadows do you think would be more interesting to explore for this class of algorithms you...
That is a great question, and I think it depends on the algorithm that you're trying to simulate. As we said, there is no one algorithm to rule them all. So for QCNNs, you need to do standard local Pauli shadows. If you want to simulate match-gate circuits, you need to do fermionic shadows. So it depends on the task that you're trying to simulate. Just like there isn't one algorithm to simulate everything, there isn't one efficient tomographic procedure that you should use. And again, for me, it's fascinating that the quest to understand barren plateaus has taken us to classical shadows and the power of data. So I think there's something very deep there that I still don't quite understand. And hopefully, you know, next year's QTML, I'm going to be like, oh, you know, you remember when I said this? But if people are interested in exploring this direction of what is the underlying cause that is the math behind all of this, I'd definitely be interested in chatting. But it depends on the task at hand, I would say.
Okay, last one, Jens, please.
Hi, Marco. Great talk. Wonderful. Can I follow up on an answer you just gave a second ago on advantages in sampling? As I mean, we all know that it's much easier to get like provable advantage in sampling problems over ones that compute expectation values. But it's not so easy to kind of turn this into a practical application of a kind. So do you have any thoughts on that, where like samples could be more useful than expectation values?
Oh, that is the million-dollar question that you're asking. I don't know. I don't know what problem sampling could be used. I've seen some exciting applications coming from some recent papers by IBM, where they try to sample some low-lying energy states that they're then putting in classical algorithms. But I don't know what is the killer app. But as you said, it's just like it's easier to prove stuff for sampling. I think that in our case, it's very hard to prove no-go results for sampling. It's just fundamentally, conceptually different, their complexities. And this is also something that maybe it's obvious for people, but in my mind, I still haven't really understood the difference in complexities. But yeah, thank you very much, and thanks everyone.
Perfect.